Thanks. Let's begin with a word of prayer. Dear Heavenly Father, we thank you for this day. I thank you for these students. Just pray that you'd help us to use this time wisely, Lord, to glorify you, Lord, in what we do. In your name I pray, Lord Jesus. Amen. All right, so I promised you guys some examples of Cauchy's integral formula. So what I'm planning to do here is just to state the formula again, which is that the mth derivative, oh man, really? What does it matter? It doesn't write. Let's see here. That's a risk I'm willing to take here. Add some color to this room. Let's see here. So f, the mth derivative of f at what? At z is equal to m factorial divided by 2 pi I believe. Integral over the boundary of d of what? F of w over what? W minus z to the, I believe, m plus 1th power dw. Now, what's the assumption here? The assumption is that we're looking at some, some domain D, and what do we have? F is holomorphic in, and let's just say near D. And when I say near D, I mean that F continuously extends to be holomorphic a little bit beyond the boundary of D. Those were the conditions we needed. Now, oftentimes when we use this theorem, and now our assumption here was what? That F was holomorphic, and in our proof, we did assume that F was had a continuous derivative, right? So the mapping Z goes to F prime of Z is continuous. We'll see at the end of today that that's actually an unnecessary assumption, and in fact that well, anyway, more on that later. So if you look at this then, right, this formula says what? If you have F is holomorphic, right, and has continuous derivatives in D, what do you get? You get a formula for the mth derivative. That's the motivation for the comment I made at the last class, which was you have, if you have once complex differentiable, you have infinitely many times complex differentiable by this formula. That's weird. But here's how we actually tend to use this, is the following. We say the integral over the boundary of D of f of z dz over z minus z naught. So I'm changing the meaning of z, all right? M plus 1 is equal to what? Well, it's equal to 2 pi I, the mth derivative at z naught of f, divided by what? M factorial. So these are both Cauchy's integral formula, but this is the one we tend to use for calculational purposes. All right, so as you're trying to think about applying this to do integrals, that's kind of your go-to. Okay? So, for an example, if I have the integral over the boundary of D, where D is about to be pictured, I haven't pictured it yet, let's say sine of z squared dz over z minus z naught squared. And let's see here. There's two cases, right? So let's say case 1 would be something like, I'll draw it over here. D looks like what? D, say z naught's out here. And, this is D. There could be some holes in it. I don't care, whatever. The point is that z naught is outside of the region, right? What's the integral? The integral is 0, right? Because this function is holomorphic on that domain. So by Cauchy's integral theorem, not formula, just the theorem we proved at the start last class carefully, this is 0. Done. Now how do I know that's holomorphic? Well, sine is sine is an entire function, right? Z squared is an entire function. It's complex differentiable on the whole. It's holomorphic on the whole complex plane. Composition of those two is still holomorphic. And you're dividing by something that's not 0. So altogether, that's holomorphic. Now what happens once you put Z naught inside D? So that's case 1. Case 2, let's say like this. Z naught's inside D, all right? D can have all kinds of holes. I don't care, whatever. D can be some kind of weird looking thing. The point is Z naught somewhere inside D. Then what's this equal to? We do what? 2 pi I divided by what? 1, right? You notice that you're looking for m plus 1 here, so it's 1 less. So it's 1 factorial, which is just 1. And then I have to calculate the derivative with respect to z of, and so I'm applying Cauchy's integral formula with what? Cauchy's integral formula with f of z equal to, looks to me like sine of z squared, right? And so we have to differentiate sine of z squared, right? And then at the end of that, plug in z equals to z naught. So what's the derivative of sine of z squared? You got yourself a 2 pi I, 2z cosine of z squared, evaluated z equals to z naught, so that's easy. 2 pi I, 4 pi I z naught cosine of z naught, quantity squared. Does that make sense? Yeah.
So what value was z naught then when you were, for the first part, you said if it was like inside something?
If z naught is actually in the domain that we're integrating around the boundary of, it's a different story.
Okay. Oh, so that's for z naught outside of. Okay.
Yeah. It would still be true, Nathan's wondering, if z naught was here.
Well, that's not what I was wondering.
Oh.
Actually, I think one of the homework problems,
Uh-huh.
I think there's something like this, but you said there were like 3 cases.
There are 3 cases. There appear to be 4 cases, but there in fact are 3. Because
One of them, like when it's on the boundary?
2 of those. No, I said it's not included. So that one in the homework, there's 2 singularities. You've got minus I and I, right? And so you're gonna consider counterclockwise loops which do not include those points. In other words, I mean that the points are not actually in the trace of the curves. I mean, they're not actually part of the point set of the loop, okay? So with that in mind, there are actually 4 possible kinds of loops you could draw. But counterclockwise. If we don't throw in counterclockwise, there are more. If we allow multiple windings, there are infinitely many. But here you got a loop like this, right? You got a loop like this. You got a loop like this, right? All of these counterclockwise, right? Because that's in the problem. And you're right, there's a 4th possibility. What is the 4th possibility? I'm putting words in your mouth. I guess you didn't say there was a 4th possibility. Search your heart, you know that's to be true. There's one other possibility. enumerating the possibilities of things that loops could either. What's the other sort of topologically distinct case? What's that? Yeah, right. Just out here minding its own business like that. And yet I say there are 3 cases in the homework problem, and I don't need to correct it. Because 2 of these cases give the same value. There are 2 ones that are 0. And there are 2 ones that are non-zero. So actually you get 3 cases. If you 2 of these lumped together into 1 case is what I'm saying. So maybe a better statement of the homework problem would be there are 4 cases. I don't know. Another example. What if we want to integrate dz over z to the 4th plus 1, right? And let's say the around the circle modulus of z minus z minus I equals to 1/2. So what's that look like? Let me call this thing C, just to have a name for it. So that C it's centered at I, right? And the circle, it's got a radius of 1/2. It's down here, right? You guys see that? Okay, we want to calculate this integral, but we don't want to calculate the integral directly. We want to use Cauchy's integral formula, all right? So the question then is, inside this circle, does that function even have a divergence? Does it have a place where you have division by 0? Is there a singularity of the integrand in there anyway? If there's not a singularity, odds are, if you can write the formula, it's holomorphic. So the integral 0. But let's see here. So the question then becomes, you see all that stuff that we talked about before test 1 still matters. Because the question then becomes, how do you factor z to the 4th plus 1, right? So you just have to find the zeros of what? You have to solve z to the 4th minus 1 equals minus 1, right? So what's that make z equal to what? So the zeros here would be z is an element of the 4th roots of minus 1, which are what? Yeah, maybe we can be lazier, right? This is actually z to the, this is actually what? This is z to the 4th, what? Minus I squared? No, I squared, right? Which is what? Z squared minus I, z squared plus I. So let me partition this off here. That would be this approach I'm putting in dots. That's a good approach for harder problems. This one probably you can just factor like you're suggesting. Yeah. Then what? Yeah. That fortunately that's actually how the half. It is in fact the case, right, that the half roots of z are equal to the set it's the square root of z, the principal square root, right? And then minus the principal square root, because the second root of unity is just minus 1. So in fact that is, so right, what that means is that we can actually either have square root of I or, I mean, what you're saying is right. So this is z minus the square root of I, z plus the square root of I, z minus square root of minus I, z plus the square root of minus I. So I don't know. I guess, is the fourth root approach better? I'm not sure. And what is the square root of I? How do you calculate the square root of I? These are all principal square roots, right? So the square root of I is the square root of e to the pi I over 2, right? Which is equal to e to the pi I over 4. So what you got here is z minus e to the pi I over 4 times z to the plus e to the pi I over 4 z minus, and what's the square root of minus I? So I rewrite the number in terms of its principal argument, right? And then the principal square root, remember, I'm using something. The square root of z is the square root of the modulus of z times e to the I arg of z divided by 2, right? That's the principal argument. I'm just using that here. So this is e to the minus pi I over 4. And so yeah, e to the minus pi I over 4 z plus e to the minus pi I over 4. Okay. Great. Those, in fact, are the fourth roots of minus 1. Every single last one of these things I wrote there, if you take the fourth power of it, you'll get what? This to the fourth power, this to the fourth power, that to the fourth power. Let me underline them. Every last one of these dudes, if you take it and raise it to the fourth power, you get back either e to the pi I or e to the minus pi I, which is what? Cosine of plus or minus pi, which is otherwise known as minus 1. Those are all fourth roots of minus 1. Anyway, it's helpful to visualize those geometrically, right? Because those are our points on the unit circle. They're easy enough to picture. So the unit circle looks like what? Like this, right? And those 4 points are at 45 degrees, minus 45 degrees. They're here, here. I'm not sure about this, actually. Here and here. I don't know. Is my picture right? I think they're outside those circles. I think it's outside the circle. How would you check?
Shouldn't your axis be below the small black circle? Or am I just going crazy?
Well, the circle I'm looking at was centered at I. Oh man! I'll fix it. Now it's centered at minus I. What's wrong with me? My goodness. How did I put I down there? I mean, what possessed me to put... This goes to a larger theme. When I do something wrong, you should say something. Last class, I did something where I differentiated the integrand and then did an argument which led us to second derivatives. That was nonsense. We were integrating f of z dz. We should have had u and v. Not... I somehow ended up with second derivatives. It was If you look at page 84 of the notes, the correct proof is there, and there is no need to look at second derivatives of u and v, as we did last class. And some of you should have told me that what I was doing was wrong. Just like now. At least 4 of you knew what I was doing was wrong here and said nothing. Ah! I think I've expressed the oddness of it. Now, that's a good question, though. So the pictures can be deceiving. Are the singularities actually inside the circle or not? How can you check that? It's pretty simple. What you need to calculate is the distance from the center of the circle to the singularity. So all we need to check on the picture, let's check if the distance from, and what would the singularity be? This would be e to the minus pi I over 4, right? So we just need to calculate is e to the minus pi I over 4 minus I, so that'd be plus I, right? What's that equal to? Well, that's the square, that's 1 over the square root of 2 minus I over the square root of 2 plus I, right? Which is what? 1 over the square root of 2 modulus of 1 minus I plus I squared root of 2. Which is 1 over the square root of 2 times the square root of 1 plus, well, square root of 2 minus 1, quantity squared. What is the square root of 2 minus 1 quantity squared? You get 2 plus 1 is 3, and then minus 2 root 2's, right? So this gives us 4 minus, I believe, 2 root 2. Can we simplify that further? I'll bring the square root of 2. Bring the square root of 2 back inside. What do you got? 1 minus 1 over the square root of 2? I think? No? What?
2 minus square root of 2.
When I bring the 1 over the square root of 2 inside, it becomes 1 over it becomes 1 over 2? Oh yeah. I'm sorry. I'm an idiot. It's not fine. 2 it's definitely not fine. Minus what? Minus square root of 2. All right, there we go. Finally. Good grief. All right, and then what? So the square root of 2 is what? 1.41 blah 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 blah. What is that?
7.
See what you guys have driven me to.
No, just leave it the way it is. It's beautiful.
It is not beautiful until we know for certain what that is. This, I want to show you explicitly, is 0.765. Now we can all recognize that that is greater than 0.5, which means that that's outside the circle. Was that a sarcastic? Or that was an actual O? Or I couldn't. Lorenzo made a face. I'm not sure the meaning of the face. Okay, anyway, so that's 0.
Use a calculator.
So what we have now shown is that, in fact, this is equal to 0 because 1 over z to the 4th plus 1 is, in fact, holomorphic on that circle. What happens if we increase the radius of the circle to 1? What would happen then? So same function. Well, here's my singular points. Now let's think about let's make it even a little bit. Anyway, I wanted to include both of those points. I don't want to think about it either. Okay. I think if I make it 1, I'm not. I think 1 includes both of those also. Let me just. All right. So. Well, you can. Let's see. Oh, this is less than 1, right? So.
Then the other one you have symmetry.
Yeah, exactly. So let's integrate around that loop. Then what do we have to do to find the integral of z to the 4th plus 1 with that loop? Actually, along the way, we found something useful. these are, well, let's see. So to do that, now the trouble here, right, is that there's two. It's not quite the right format to use, right? Cauchy's integral theorem, because this thing has two singularities inside the loop, right? So either we need to, somehow deform the loop into two loops and add them together, or we need to do what? Change the function so that it's the sum of two functions, each of which has only got one singularity. So that's what's called partial fractions. So I think, let's see here if I can think of this. So we've got z squared minus I over z squared plus I. I think I'm going to use the other idea rather than, we'll talk about partial fractions some other day. It's going to take me about 5 minutes to convince myself to get to that. So let's instead look at it this way. If I took this circle and this circle, right? Let's say this is gamma 1 and this is gamma 2, right? It's clear that this function, 1 over z to the fourth plus 1, is holomorphic between these purple circles and the red circle, right? So by the deformation theorem, I have that this is equal to the integral over gamma 1 of dz over z to the fourth plus 1 plus the integral over gamma 2 of dz over z to the fourth plus 1. Because basically those, I'm giving those counterclockwise orientation because that's, yep.
What about the rest of the circle?
The rest of the circle.
Yeah, don't we have to integrate over the whole circle?
Well, my point here is if this outside circle is gamma,
Like those are just two little parts of gamma though. What about the rest?
those aren't gamma at all. Those are inside. But I can.
Right. But you're saying that gamma, or the integral over gamma, equals the integral over gamma 1 plus gamma 2.
Yeah.
Or plus the integral over gamma 2.
Basically, the argument is something like this. So gamma you can break up into two pieces. It's this piece up here, right?
Right.
And then you could say then it's this piece. Then, well, how to say this? It's this piece, right? And then I think about, got this piece down here, like that. On the flip side, I have, let's see here, this piece, and this piece, and this piece, and this piece. And the reason I can argue that these integrals are equal to those integrals is because I can add crosscuts to connect them, like this. So the black arrows cancel out when you add the integrals, and it will show you that the integral of the inner loops is equal to the integral of the outer loops, assuming that you have the holomorphic condition in between.
Okay.
This is an application of what I more generally call the deformation theorem, which basically says that the integral around the boundary is responsible of the interesting integrals in the inside summed together, basically. Here there are two interesting spots, the two singularities at plus or minus. Well, e to the minus pi I over 4 and e to the, what is that?
So then if there were
Pi over 4.
If there were no interesting spots, the integral would just be 0, correct?
Indeed, as in our original setup, yes.
Okay.
Now-
That's starting to make sense.
Okay, so this is what? I mean, this is actually the integral over gamma 1 of what? Well, what's the troubling? The troubling thing in gamma 1 is 1 over what? 1 over z minus what? Which is 0 inside gamma 1. Which one of these is, let's see here. I think that one, because it's this one. All right? Because, oh, rather plus, sorry. Because this is equal to 0 right there, because that, see, that's e to the pi I over 4, this is e to the minus e to the pi I over 4, right? So this term is 0 at that singularity inside gamma 1. And then you have everything else, right? You have the, 1 over the other 3 terms. All right? Let me call it Pac-Man, Ghost, and Dead Ghost. Okay. Here's Pac-Man, here's Ghost, here's Dead Ghost.
Why those three? Why not the plus?
Because this is the one that's 0 inside gamma 1. And so I want to use Cauchy's integral formula, right? And I'm identifying this as being the holomorphic piece. So this is my f of z to use. But on the flip side, the gamma 2, I've got 1 over what? Well, what's the offending factor? The thing that's singular right here is what? Z minus e to the minus pi I over 4. And let's see here. I guess I need to I'll make this be a stick figure. And so you've got stick figure. Well, actually, you got Pac-Man. You got Pac-Man. You got, what do you got? Stick figure. It is not Abraham Lincoln. It is stick figure. And you got Dead Ghost. I'm going to ignore that. And the point is, that function, which is just the reciprocal of those factors, is holomorphic, right? Inside gamma 2. And then how do we finish? Well, we use Cauchy's integral formula, and this is the easiest one. Thank goodness that we're using the m equals 0 case, which means we don't have to differentiate, we simply evaluate. Right? So then you just have to plug in what? So what's the z naught in this case? Minus e to the minus pi I over 4, right? And z naught in this case is e to the minus pi I over 4. That's the thing that makes that factor 0, and that's what you have to plug into the remaining holomorphic function as you apply the m equals 0 Cauchy, generalized Cauchy's integral formula.
Wait, are you supposed to have e to the pi over 4 on the rest? You don't have a minus in your integral.
Oh, thank you. See? That was helpful. Thank you. And so what do? M equals 0. We still got the 2 pi I, right? But we just do 2 pi I times what? 1 over, how's it go? Minus e to the pi I over 4 two of those, right? Yep. That's the Pac-Man term. Ghost term, I get e to the pi I over 4 minus e to the minus pi I over 4. What's dead ghost? E to the pi I over 4 plus e to the minus pi I over 4, right? Then what? Plus 1 over do. And now we do Pac-Man at e to the minus pi over 4. So e to the minus pi I over 4, what was the Pac-Man term? Minus e to the pi I over 4, right? And then stick figure. So I do e to the minus pi I over 4 plus e to the pi I over 4. And then what? What am I on? Oh, dead ghost. So this time, 2 e to the minus pi I over 4, right? Ah, yes, good point. So I'm missing, I'll put it in green. There's a minus here, right? And here? Mm-hmm. Now, was there anything else? You guys can understand this. I mean, I would be a monster to test on this if I didn't think you could understand it. I'm quite certain all of you can understand this. I mean, this is a pain, right? This example is a pain, but I'm missing a 7. Thanks, Joe. Thanks a lot, Joe. Joe. This can be simplified, right? I mean, I'm not joking. This actually can be simplified quite a bit. What happens when you, you should recognize that this is like minus cosine of pi over 4 times 2. You should recognize that this is 2i times the sine of, minus 2i times the sine of pi over 4. And over here, you've got minus 2i, the sine of pi over 4. And this term is the cosine of pi over 4 times 2. So those give you like a half. I mean, so that collapses down to what then? 1 over root 2, 1 over root 2, right? You multiply them, that gives you a half. The half cancels. So this all simplifies down to minus 2i. This all simplifies down to minus 2i. This is what? Minus 2e to the pi I over 4. This is what? Let's see here. So what we have is 2 pi I times 1 over 4i e to the pi I over 4 plus what? 1 over 4i e to the minus pi I over 4. If If you disagree, let me know. Mm-hmm. Certainly. So, yeah. So I got a pi over 2, right? And let's see here. I feel like we should make a common denominator, yeah? So this is e to the minus pi I over 4 plus e to the minus pi I, e to the pi I over 4 rather, divided by e to the pi I over 4 times e to the minus pi I over 4. I did that right. Let me think about that. Yes, no?
Hold on. More.
So the answer is pi over 2 root 2. Oh, just pi over root 2. Sorry. Yeah. See what I did? Of course, this goes to 1, right? And upstairs, you have twice the cosine of pi over 4, which is 2 divided by root 2. The 2's cancel, you get pi over root 2. That's good? Okay. So, I mean, there are, as you can imagine, many, many variations of these. I mean, you can pretty much write down any function you can think of, and the problem of integrating it really just becomes a problem of figuring out where the denominator is 0, and figuring out then how can you factor out a copy. You know, can you factor out the z minus z naught in order to apply the theorem, right? All right, so I think I spent too long on that example. Sorry about that. But I think it's important for you guys to see some long-winded examples from time to time. So what I will show you in the remainder of the time is Liouville's theorem. I hear different people. Some people say Liouville, some people say Liouville. Louisville, yeah, I've heard that too. Your guess is as good as mine. Do you also make? I don't know. I'm fairly sure he's dead. Okay, but let's see here. I mean, he might be a ghost. No. Okay, so the idea of this is one of those theorems which I don't mind asking you guys to prove on the exam, because it's pretty simple to prove this theorem. It's a simple. You can derive it. Basically, it's a simple derived consequence of Cauchy's integral formula. All right, let me show you how. So we start by assuming we have a holomorphic function on some closed set D, and then there's some slightly larger set, say D tilde, on which it's also holomorphic. All right. And then we consider, you know, again, a function where both the function f of z and the derivative f prime of z exist, and we're also going to assume that the derivative is continuous. Next class, I'll explain to you why that's an unnecessary assumption. The continuity of the derivative itself is automatic by Gorsaz's theorem. But anyway, so Cauchy's integral formula applies, and we get the mth derivative at z naught is equal to m over 2 pi I, such and so forth, right? And we're looking at a disk of radius rho, all right, centered at z naught inside this closed set D, right? Of course, you can parameterize a circle, right? z equals z naught plus rho e to the I theta. And if you do that, this z minus z naught to the m plus 1 factor, like we worked out the other day, it just breaks back to the radius times e to the I theta to the m plus 1 power, right? But you can use de Moivre's theorem, probably mispronouncing that too, to rewrite that as e to the m plus 1 times I theta power, right? And so one of the e to the I thetas cancels with that e to the I theta, and then the mth power of it factors out for the rho, right? And you're left with a e to the minus m I theta up here. We good so far? I mean, it's a pretty straightforward calculation. Now, if you have an addition that the modulus of the function is bounded on that circle, right, by some m, then you can use the ML theorem, right, to say that the modulus of that integral is less than 2 pi m. See, because this is just something unit modulus, right, that's on the unit circle. And so you just have this, and so there you go, by the ML theorem again. And so that gives us what's known as Cauchy's estimate. Cauchy's estimate says that if f is holomorphic with continuous derivative on the domain D, then for any closed disk on which f is bounded for all z on the boundary, all right, so the bound doesn't have to be for the, you notice that the bound f of z less than or equal to m, I don't have to have that for the whole disk. I'm actually saying that I just have the bound on the actual circle, the edge of the disk, which is nice when you're trying to set up a bound and apply this thing, right? Anyway, you find that the mth derivative of the function as z naught has to be less than or equal to m factorial over rho to the m. And that's just this. Basically, take the modulus of Cauchy's integral formula, and that you get, right? So that's supported by the thing we looked at in the last page. But anyway, that brings us to Leibel's theorem, which says that if f is holomorphic with continuous derivatives on the whole complex plane, if the modulus is bounded on the complex plane, then the function's constant. So bounded entire functions are constant. So proof is this: if you have f and f prime of z are continuous, and if you have the modulus of f of z is less than or equal to m, you can consider an arbitrary disk of radius r centered at z naught. You use Cauchy's estimate with m equals to 1 to get the modulus of the derivative is less than m over r, right? And then you just let, you let r go to infinity, and you see that the derivative at z naught has to go to 0, right? But z naught was arbitrary, so you've just shown that the derivative is 0 everywhere, but the complex plane is connected. If we have 0 derivative on a connected set, it has to be identically what? It has to be constant, right? We proved that earlier. So then it follows that f of z is just equal to c for some constant. And this is Leibel's theorem. Now, some of you copied my solution to the fundamental theorem of algebra proof from last year, right? Where we used Leibel's theorem to prove that if there was no 0 to a complex polynomial, you get a contradiction, right? Basically, the argument was if there was a 0 to p of z, then 1 over p of z has a divergence, right? And so if you have 1 over 0, you can basically argue that the modulus has to approach arbitrarily large values as you approach that singularity. And so if that's not the case, then 1 over p of z is bounded. If there are no zeros in the polynomial, then 1 over the polynomial is bounded. Now, actually showing that is a little bit subtle, right? And I still owe you guys a 15-minute add-on to the course about inequalities, but I'll do that sometime soon. Anyway, so again, the proof of Cauchy's estimate is really just this combined with Cauchy's integral formula. Anyway, if you don't understand that, we can go through it again in another day. But next class, I'll pick up at Moreira's theorem and Gorsat's theorem, and we'll talk a little bit about z and z bar. Thanks, guys.